3, 2, 1, go.
Good day, grade 10s, and welcome to week 6 of the program, but I think it's like your week 5, maybe, I can't remember. But today we are going to relook at electricity. Okay, so last time I saw you guys, we did electrostatics, if you remember correctly. Okay, so we're just going to recap electrostatics. I hope you guys did the homework problem I gave you. And then we are going to talk electricity. Okay, now today you do not need a textbook in front of you. Okay, I'm not going to be doing stuff that is in the textbook. Right, today I'm going to be doing basics of electricity. Okay, just so that you guys have a very solid background in terms of electricity. Okay, and then tomorrow we're going to start with the theory of electricity. Okay, right. So just very briefly, we're going to revise electrostatics, and then we're going to look at the electricity basics. Okay, guys, I am going to switch over to my ever favorite whiteboard. Ma'am, I'm breaking up again. Okay, give me a second. Thank you for letting me know. Is that better, guys? Okay, cool. Guys, it seems like my microphone might just need a reset every now and again. Hello, Jared. So if I do break up, just pop it in the message. Okay, I've got my chat open in front of me so I can see you. Okay, and just let me know. Just remind me every now and again. And then we just take a quick stop and we restart it again. Oh, Nelly, I missed you guys too. Hello, Tyrese. Welcome, everyone. Okay. Right, guys. So on Thursday, I keep on wanting to say Friday. How's that? Okay. I keep on wanting to say Friday because it was the last day of the week, but it was indeed Thursday. Hey, right. So what we did on Thursday is we talked about the idea of quantization of charge. Yes, I am officially back. I am hanging on to you guys for as long as there is a lockdown. Okay. You guys know we can't promise beyond that. Okay. But I'm going to be here until I have to go back for my matrics, okay? And I will tell you before that happens, all right? I'm not here to joke around with you, and I'm not here to not tell you what's going on in life, okay? So for now, okay, I am going to keep you guys. I have given up the grade 12s to a really cool teacher, but Mr. Chris just had too many connection issues. And so I decided I didn't want to throw you guys to wolves again. Okay, you are my peeps. I enjoy teaching you. Okay, I'd love to be able to teach all the sciences, but I'm only one person. I have a lot of admin to do too. Anyway, so let's get back to the work, people. Okay, we did quantization of charge. Okay, and we said all that means. Ollie the rainbow pen. Oh my goodness, you guys are insistent. Okay, so we did quantization of charge. Okay, and we said that all that means is for every quantum, it has a specific number unit. Okay, and then we said that for electrons, that quantum is 1,6 times 10 to the power minus 19 coulomb. Okay, so each electron has a charge of 1,6 times 10 to the power minus 19. And because electrons are negative, we can put the negative sign in front. Okay, then we spoke about what happens when an object gives up an electron, and what happens if an electron is added to an object. Okay, so we kind of had a look, and then we finished off here. And we said, well, I've got two objects, A and B, and A has a charge of +3 microcoulomb, and B has a charge of -1 microcoulomb. And I told you guys that micro, that funny sign there, simply means that it's 10 to the power -6. The other thing that you are going to see in electrostatics and electricity is nano, and that's quite an easy one because nano is -9. Okay, so the problem I did with you guys is we looked at, if I touch A and B together, what will their final charge be? Okay, and we said that their final charge is A plus B divided by 2. So we did all of that, and we got that the final charge on both A and B is +1 microcoulomb. All right, and then the question that they like to ask from there is, how many electrons were transferred? Okay, so we said when we looked at A, the initial charge on A is +3 microcoulomb, and the final charge on A is +1 microcoulomb. And we said, that we use the idea of change in charge to calculate how many electrons moved. Okay, so I said the change in charge on A was -2 microcoulomb, and we used that change to calculate how many electrons A gained. Okay, so I asked you to have a look at the same problem for object B. Okay, I'm going to try and do this in the Galaxy pen. It might fail horribly, but we're going to see. Okay, so, and it's just for Ollie that I'm doing it in the Galaxy pen. Okay, so the change in charge is equal to the final charge minus the initial charge. Okay, and we said final charge on both is +1 microcoulomb. And then, I'm glad you guys like the change of scenery. Whoop, come back here. Then the initial charge on B, we're working with B, was -1 microcoulomb. Now you have to be careful because there is a minus in the formula, and then there is another minus for the charge. Okay, so that minus is the initial charge, and that minus there is from the formula. Okay, that means that the change in charge on object B, +1 minus times a minus becomes a plus, becomes +2 microcoulomb. Okay, not that hard. And now we say that the change in charge is equal to the number of electrons transferred times the charge of each electron. Okay, guys, all with me? I just calculated the change in charge. Remember now microcoulomb, so 10 to the power -6. I want to calculate how many electrons, and we said that the charge of an electron is 1,6 times 10 to the power minus 19. And because it's an electron, we make it negative. Okay. So now we have to do some mathematics. Okay, we're going to take this 1,6 here and divide it that way. So I'm going to end up with this mathematical thing here. Okay. I had a calculator not too long ago. It's not grand feet. Aha, it was hiding under a piece of paper. So 2 exponent minus 6 divided by 1,6 exponent minus 19. Oh my goodness. And I get try that again. I get 1,25 times, oh, it's minus 10 to the power 13. You don't have to view in the YouTube feed. We're simply telling you where to get it. Okay. Right. Dunk, dunk. Right. Now, it is the same answer. Can you see that? It's the same answer we got for the amount of electrons that was gained by A. But it is a negative number. That means that B lost 1,2 times 10 to the power 13 electrons. Okay, so let's think about that. Does it make sense in terms of what we spoke about earlier? Okay. No, other way. There we go. All right. When we started, we said that B had more electrons. It had an overload, an excess. And A, because it was positive, had a lack of electrons. So the electrons would go from B to A. Okay. Don't worry about it, little trouble. We're just catching back up from what we did on Thursday. Okay. So electrons went from B to A. All right. And that makes sense in terms of, I'm just trying to get them on the same page. I know they're tiny. I apologize. That makes sense in terms of this. Now, Jared, I did see you pop up here. But now I've lost you. Where's Jared? Guys, we've lost Jared. Oh no. Ah, Tyrese snap. Okay, so when we have a Jared back, we're going to have to ask a Jared to explain the calculator thing. Yeah, Ali, we've had like serious connections. Even the teachers have been having problems. Okay, so I actually don't like it. It makes complete sense. I think there's something in the cloud, you know, like the virtual cloud. Okay, so guys, this is very, very basically what happens in electrostatics. Okay, we have two charged objects. Okay, and then we touch them together. They share the electrons evenly between the two of them, and then we can calculate what is the final charge on both objects, and we can calculate how many electrons was transferred and from which one. Okay, so that is very basic electrostatics. All right, in grade 11 you deal with forces in electrostatics. Okay, so don't have to panic. Okay, I promise it's not that hard. And the electrostatics that you do, Coulomb's law, you know that C there, Coulomb's law, you will carry into grade 12. Okay, so grade 11 electrostatics builds on this. Now that's the number one thing that I think people forget. They forget about these teeny tiny little equations. Okay, so the electrostatics, these ideas of two objects touching each other, transferring electrons, okay, and then being able to calculate the final charge on both, as well as the number of electrons that got transferred. That idea is what you definitely, I know, Miss P, this is confusing. That idea is what you need to know about electrostatics. Okay, so last time recap, electrostatics. You need to know that when two objects are charged and I touch them, the electrons will spread evenly. And so the charge on the two objects after I've touched them will be the same. Okay. And that I can calculate the number of electrons that gets transferred from one object to the other. Okay. That is basically what you guys need to take away from this. Okay, now I'm going to teach you electricity in such a way that when they ask you weird and wonderful questions, you can answer them. Okay, because if you understand the basics of electricity, then the harder parts of electricity is not that hard. Okay, now some of this might be very boring and some of you might go, duh. Okay, I get that. Okay, but I want you to try and focus with me today, because if you can get the stuff in this, then I can guarantee you electricity is going to be like super easy. Okay, I promise. Okay, so when I have an atom, okay, especially a metal atom. Yes, Zelne, that's why I moved over. Okay, and let's go back to like a normal color so I don't fry your brains. I will use the cool, funky colors to highlight stuff. How's that? Okay, so I have an atom, okay, metal atom. So in the middle, I have protons and neutrons and more protons and more neutrons, okay? And then around them, I have these electrons, okay? And when I have metals, the electrons are what we call delocalized. It's a little bit of what I'm doing, okay? I'm in Cape Town. That is my local place. But D, away from, I can teach away from my local place. Okay, so delocalized electrons means that this electron does not belong to this atom anymore. It is free to move. Okay, now, when you have no energy, like none, like I think you guys might be feeling right now, are you going to voluntarily run somewhere? Like, are you going to voluntarily get up and go and do like serious exercise when you have no energy? Think about when you finish writing an exam, or you've been spending a whole day watching online stuff, and your teachers at school has been giving you information, and. No, there is no way you are going to go anywhere. Doesn't mean that you don't exist, okay? It just means that you are not moving, okay? And that is the crux about electricity, okay? So electricity, you don't have to write this down, just follow, is movement. movement of electrons. Okay. More specifically, in the fancy word they use, it is the flow of electrons. Okay, so when I have a copper wire, okay, the thing that electricity flows through, the electrons are already there. They just have absolutely no energy. And so they won't flow. Okay? So when I am holding a copper wire in my hands, uninsulated, and it is not attached to something that gives those electrons energy, they are still there. They don't now suddenly disappear. They are still there. They just don't move. Okay? And because they don't move, they have no energy. Okay? Electricity, the thing that hurts, nah? If you touch an open wire and you get that shock you feel is the energy of the electrons being transferred to you. Okay? It's not the electrons, it's not the battery, okay? It is the energy that the electrons have that flows to you and gives you that shock. Cool. So, what thing do we use in an electrical circuit? There's more than one right answer. That gives energy to these electrons. That say to the electrons, hey, come, move, go. There's more than one right answer, guys. So what thing do you think we have that gives electrons energy? Come on. Come on. Where are you guys? Wrijving, good one. So Corley said friction. Come on, guys, take a guess. Like, I don't care if you're right or wrong. Come on, anyone else? Give me an idea. Come on. I'm not speed feeding you. Static, a battery. Here we go. Here we go. Here we go. So Ashley, yes, that static, okay, is from there being more electrons in one place than in another, okay, and they then exert a force on each other, right? They like make each other jump, okay, they push each other. So Tyrese, the question is, what do I put into a circuit? What do I touch to a metal, okay, if I want the energy to go to the electrons, if I want to give the electrons energy, okay? And so guys, the answer that I was looking for came here from Aston and Anke, okay? And I'm looking for a battery, okay? Now, we also refer to batteries as cells, okay? So actually you weren't wrong, okay? Because that is like a form of energy, okay? That is what makes the static energy go, right? You're not wrong. So in electricity, right, I'm talking electrical circuits, we have cells. And if I have many cells, I call it a battery. Okay, so that is the difference between a cell and a battery. Okay, a cell, think about when you're eating a lemon or a orange, okay? One cell is one block, and many blocks give me the whole orange, okay? So cell is one, and many cells is called a battery, okay? That's just one language thing that they sometimes stupidly finicky about. Okay, so now, this cell or the battery has energy. So I've got an electrical wire, And now I add a couple of cells or I add a battery. That is the symbol for 3 cells. We'll get to the theory tomorrow. You don't have to worry about it now. Okay. Who says that the electrons that are already in this wire here, you see there they are already. Let me remind you, there they are already. They are part of the atom. Okay. Who says that these electrons will now move? Just yes or no. Yes, no, yes, yes. I'm getting, yeah, I've got a couple of no's. I just want yeses or no's. No. Okay. Those who say yes, are you saying yes because the electrons are now given energy? Yes. Okay, I thought so. Right. Cool. Now, if I give you a Red Bull to drink, I don't know how many of you are like me, sugar infused, okay? And I know Red Bull's bad for you, okay? Just bear with me. I give you a Red Bull to drink, and I tell you to go. What is normally the first question you ask me? Most of you would go where? Where do you want me to go? There we go, Miss P. Where? Okay? And the problem with these electrons is, yes, they have energy. Okay, Tyrese, you exactly started it right. Good job. These cells now have energy, but they have nowhere to go. Because the second this electron tries to run that way, it goes into thin air. Okay, it can't completely disappear away from the system. And so the electricity will not flow simply because the electrons have nowhere to go. But the second I give these electrons a closed loop, remember all of this wire is metal and all of the metal already contains electrons, okay? So now I have given the electrons a path. I have told the electrons where they can go. Okay. So that is the 2 things that you have to, when you want electricity to flow. You need an energy source and you need a closed circuit. Okay? Electrons are really stupid, like really stupid. They can only run within a closed circuit. They can't run somewhere else. Okay? They haven't got enough intelligence to go, ooh, well, I could go left, I could go right. They can only run in a closed circuit. Okay? So even if you give them energy, if you don't show them exactly where to go, they won't go. Okay, so that is the 2 things you need for an electrical circuit. You need an energy source and you need a closed circuit. You need a path. Okay, but I want you to know and to remember and to understand that the flow of electrons, doesn't come from the cells or the battery. That is the number 1 misconception that people have in electricity. The electrons are not given by the cells, okay? The metal already has all the electrons in. The cells simply give it energy. Okay, that is like a super, super, super important part, okay? Now, in electricity, we have 2 concepts, okay? We talk about volts. Okay, we have 3, but I'm going to deal with 2 now. We talk about volts and we talk about current. Now, volts could also be called potential difference. Okay. So volts tells me how much energy each electron has, and current tells me how fast they run. Okay. Now, it is true that the more energy an electron has, the faster it can flow. Okay, to say that again, the more energy an electron has, the faster it can flow. Miss P, yes, we're doing circuits. But we're not doing like circuits. We're doing basics of circuits. We're doing the stuff that you won't find in a textbook. Okay, right. So the cells or the battery tells me how much energy. It does not tell me how fast the current flows. Okay, I need a different way of measuring that. So look at this definition, potential difference. Okay, so when we measure volts, when we measure energy, we don't actually measure the exact energy. We measure the difference in energy between 2 points. Okay, I'm going to say that again. When I measure volts or energy, we measure the difference between 2 points. Avela, the basics of this, I will give you guys the theory tomorrow that is in your textbook, I promise, okay? But I just know from experience from teaching it for a couple of years, okay, that there's a couple of things that you guys misunderstand about circuits, okay? So don't worry, we guys are going to get to the maths tomorrow. Don't panic, okay? I want to just talk about the basics, the stuff that I think is not put enough emphasis on. Okay, so potential difference. So when we measure volts, we measure not the energy there or the energy there. We measure the difference in energy between 2 points. Okay, I'm going to say that again. Volts is the potential difference, the energy difference. So when I measure volts, I have to measure the difference between 2 points. And so voltmeters are always in parallel. Okay? They are always outside of the circuit. They are always over the thing we want to measure the volts from. Okay? But current is how fast, how many electrons run through a point at a certain time. Okay? I'm not measuring how many electrons are there between there and there. No, I want to know how many electrons go through that point there in a specific time frame. And so when I measure current, okay, I measure in series. Whoops. Okay, or we use the word, oh, that's terrible, guys, sorry. We use the word through a point. Okay, you'll often see me refer to the difference between through and over. Okay, that is pretty important when we are working with electricity. Okay, guys, so the cell does not contain the electrons. The cells contain the energy. Cool? The electrons are already there. They're already in the metals that I'm dealing with. Okay? I must just give them energy to flow. And the other thing that I have to give them to flow is a closed pathway. So this is a favorite question they like to ask. What two things are needed for electricity to flow? There you go. You need an energy source and you need a closed circuit or a closed pathway. Okay? Then the other important thing is the difference between volts or potential difference and current. Okay? And we are going to start looking at volts and current in depth tomorrow. Okay? So the potential difference or volts is measured in volt, and the current is measured in very posh ampere. Okay, French word. Okay. And for some other bizarre reason, although ampere is shortened to A, current is shortened to I. Now, I don't know. I wasn't there when this was designed. Okay. V, volts, is shortened to V, and volts is in V. So that's okay. It's just this one that's a bit different. Okay. Ollie, it's okay for electricity to make you tired. This is very new. Okay. I know you guys did this in grade 9. Yes, Tyrese, the triangle diagram. Boom, boom, boom. Okay. I know you guys did this in grade 9, okay? But you probably like sped through it and no one actually took the time to explain to you why a voltmeter has to be over something and an ammeter, you measure the electrical current through the ammeter, okay? And why you need an energy source and why you need a closed current. Do parallel series connections produce the same current? That is a very, very cool question, Avela. We are going to deal with that not tomorrow, but in this week. Okay? Poppy, yes, we are going to look at resistance. Okay? And I'm going to explain resistance to you just like I explained energy going to an electron. Okay? Because again, if you can understand what resistance means and why it changes the current and not the volts from the cell, okay, it makes your life so much easier. All right. So guys, this week we are going to we're going to tomorrow look at current and or potential difference. All right. That's Tuesday. Then Wednesday, we are going to look at resistance. Okay, what does resistance mean? How can I calculate resistance, etc., etc.? Okay, and then that's Wednesday. On Thursday and Friday, we are going to get stuck into the difference between series and parallel circuits. Okay, now I've got good news and bad news for you. Good news, like always, okay, we're going to explain it until we are blue in the face, until everybody gets it. I promise. The bad news is that there are some bits of electricity and the rules in electricity that almost no one understands, that almost no one can tell you this is why. The reason we can say this is why is because scientists over years have done experiments over and over and over and over and over again and seen that they are always true. Okay? And they have an idea of why. Okay, Palesa, sorry. Let me quickly wait. Okay, I'll repeat. I'm going to explain to you the rules of parallel and series circuits. But I can't give you an exact reason why these rules work. Okay? I do know that they do work because just like lots of scientists before me, I have done experiments and I've built circuits and I've measured and measured some more and measured some more. And these rules are always true. Okay? I know that that is very frustrating, but that is one of those bits of science that I think will eventually be figured out. Like, I think eventually we will truly understand why current works one way and the volts work another way. Okay, so I'm sorry, but I am going to have to give you rules that I cannot explain to you exactly why. I can give you an idea, okay? But there is no exact reason for that rule always working. But from doing the experiments, I can promise you that they do. Okay, guys, just a quick recap, just the important bits. First of all, electrons are already there. Okay, I don't have to add them. They are already in what just happened. What? Miss P, what just happened? What? Okay. Recap. Electrons are already there. The metal. Oh, whoops, are you back though? Okay, let's recap this lesson, guys. We've got like 4 minutes left. I don't want to leave you hanging. Okay, so electrons are already there. They are in the metal that the wire is made up of. The reason the electrons can flow is because they are delocalized. Okay, delocalized. They do not belong to any particular metal atom. How do they specify how many electrons are in a circuit? That is not an easy question because we don't measure actual electrons in a circuit. We measure the flow of electrons in a circuit, and we measure how much energy do the electrons have in a circuit. Okay, you could work that out by mass and stuff, okay, but that is not the focus of electrical circuits. But I agree with Ollie, that is like a really good question. Well done. Okay, so electrons are already there. The cells, the battery I add, just gives those electrons energy to move. But unless I tell them where to go, they're not going to go anywhere. Okay, they might bounce up and down like crazy things, but they're not going to go anywhere. So for electric circuits, I need an energy source and I need a closed system. I have two ways in describing the electrons. I can describe them by their energy, or I can describe them by how fast they flow. When I use energy, I can only tell the potential difference. I can only tell the energy difference between 2 points. And so voltmeters are always in parallel. So they're always over something. For current, I want to know how fast, how many through a point. And so ammeters are always in series, and I always measure whatever goes through them. Okay, guys, the other stuff with electricity, we will get to tomorrow. Okay, so tomorrow I'm going to give you the theory, so the definitions and all of that. Okay, I am going to set it up tonight, right? It's just been a bit of a crazy day, weirdly. I'm going to set it up tonight in a PowerPoint and a Word like I always do. Okay, I'm going to pop it in the drive. Okay, I will give you the drive details. I just want to get to that question, ma'am. No parallel over there, no volts. Okay, so a voltmeter cannot measure anything if you put it in series. There will be volts, okay? There will be potential difference, but a voltmeter cannot measure if you put it in the series circuit. A voltmeter is designed to measure the difference between energy of 2 points. Okay, I'm glad that helps. All right, guys, so tomorrow we're going to do definitions, okay? And we're going to look at these two concepts and how they get to definitions and calculations and all of that. No? Then resistance. Viva la resistance. And then we're going to really dig into series and parallel circuits. Okay. And I might go slower than you think I should, but I'd rather have everyone on the same page. Okay. Right. Deal, guys. So I'm going to see you tomorrow for theory. I'll see you guys in, no, I'm not seeing you in maths. Okay, guys. Have a fantastic day. Will this lesson be on YouTube? Yes, Tyler. Plus, for the JGM kids, I will send you the links as well. Cheers, guys. Bye. I will see you tomorrow.